Okay, so the Suita conjecture, therefore, Suita is thus equivalent to the estimate that pi times the Bergman kernel along the diagonal is greater than or equal to the fundamental metric. Okay, so at this point, maybe it's nice to do an example. The simplest example, of course, you can imagine is the unit disk, and it's also the most illuminating, and it will also secretly make an appearance at the end of the proof. So in this case, this is our x, and the Green's function, g of z zeta, is log modulus of z minus zeta over 1 minus zeta bar z. So your log mod z minus zeta is on top, and then you have minus log 1 minus zeta bar z. You can already see the potential along the diagonal for the Bergman metric up to a constant. Right, so then, in this case, I leave you to do the calculation. So omega f, the fundamental metric, will be square root of minus 1 over 2 dx wedge dx bar over 1 minus mod x squared z, or x. There's fewer z's than x's. I erase the least, the least I can. Okay, so this is what I would like to show you how to prove using Berndtssons theorem. I want to prove this inequality, okay? So, setup for using Berndtssons theorem. Okay, so the manifold X that we had this morning will just be our Riemann surface. And we start with omega being any Kähler form. Any Kähler form for defining our L2 spaces. Could be the fundamental metric, but doesn't have to be. The line bundle L that we have will be the canonical bundle. So we're going to be looking at one forms. And now we need a family of metrics for this line bundle. Okay, so the family of metrics, e to the minus phi sub t, will be defined as follows. So the metric e to the minus phi 0 will just be, I'll write it as 1 over omega. So, you know, the omega is a metric for the tangent bundle, so 1 over omega is a metric for the cotangent bundle, which is what this is, okay? So, in particular, notice that the Ricci of this guy, so Ricci of, sorry, I should say the curvature of this metric is just the negative of the Ricci curvature of omega, okay? So the condition in Berndtssons theorem will be a little simpler than usual. Okay, and now I have to tell you what the rest of them are. So phi tau of z will be this phi 0 of z, which is basically the logarithm of this negative, phi 0 will be the logarithm of omega. And then I'll add the real part of tau. And then I'm going to take p. P is a positive number, which is going to eventually be huge. Okay? And then you take the max of these two functions. So you take twice the Green's function at x on z minus the real part of tau, or 0. Okay? So it means that when the Green's function, so x is now a fixed point in the surface. So you have your the surface and there's some fixed point x, and the Green's function is doing, whatever, going to 0 out at infinity. should write x for this point. So and eventually in the proof we're going to let t be the real part of tau. The imaginary part will never enter into the proof. So if say the real part of tau is very, very negative, then you're looking for when the Green's function is less than the real part of tau over 2. So that means you're very, very close to the pole. So you're just in a very small region. Maybe it looks like that. So this would be, let's give this region a name. So x sub t is the set of all z in x where g sub x of z is less than, maybe 2g sub x is less than t. Okay. So it's some region. In fact, actually, if you let t go to minus infinity, eventually this thing will just look like a disk. Okay. Okay. What about the domain omega on the base of the family of manifolds? Well, this is going to be the disk, but I'm going to use the left half plane model. So this is the set of all tau in C, such that the real part of tau is negative. And now we need a holomorphic section. So maybe I'll quickly remind you. So basically, for each t, you have this weight phi t, and you have a Hilbert space h phi, say, tau. And now you want a family of linear functionals, c tau, which pairs with a function depending holomorphically on t to give you a holomorphic function. So c sub tau of f tau is holomorphic in tau if f sub tau is holomorphic in tau. That was the hypothesis for Berndtssons theorem, and the conclusion is that the log norm of this c tau with respect to the dual norm on this space, this is subharmonic. Okay, so now I have to tell you what this c tau is. C tau so let me first, let's fix some v in the tangent space Tx of this point, this fixed point x. And we can actually choose it such that the fundamental metric assigns length 1 to this vector. So the unit vector with respect to the fundamental metric. Okay. And then we define C of F. So F is in this h phi tau. It's going to be f of x divided, or maybe acting on v. Remember, f is a 1-0 form, so it can act on a 1-0 vector, right? Same as the 1-0. And so this is a number, and we want to compute the norm of this C. This, by the way, is the holomorphic form that we had as an example in the other case. So this actually, if f varies holomorphically, then clearly this varies holomorphically in T. Okay, so what is the norm of this T star? It's the sup over all f in h phi sub t, so that the norm of f squared t is 1 of c of f. Right? It's just a standard definition. And so in this case, it's just the sup over all f in this space with the norm equal to 1 of the evaluation f of x squared. And then the norm squared of v is basically 1 over the fundamental metric. So this is exactly the norm of this one form with respect to the fundamental metric. T tau. Yeah. I'm just going to be using it for real parameters anyway. Okay, and now this was one of the either exercises or something like that, that this is actually the Bergman kernel. So this is exactly B sub x of, well, it's not, I shouldn't say that. It's the Bergman kernel for this Hilbert space. So it'll be k sub t of xx divided by the fundamental metric at the point x, okay? And if you, so at time t equal to 0, this is actually our b sub x. Okay, so let me write that down. So maybe I should show it here. So at t equal to 0, this thing here is just, the Green's function is always negative, so the max of 0 and something negative is 0. This is 0, and so you just have your phi 0. So that's the initial space, which means that the resulting Bergman kernel is this one that we discussed here. What was the notation I was using there? Let me just write it down. At t equal to 0, norm c squared 0 star. This is not literally defined because 0 is in the boundary, but you could make it a little bigger if you wanted to. So this will be bx of xx over omega f of x. So this is the quantity that we are trying to determine, right? And now, by Berndtssons theorem, this log norm c squared, so it's supposed to be a real part of t, but a real part of tau, but that's just t. Sorry, it's supposed to be tau, but it only depends on the real part because the norms only depend on the real part. You look at the only real part of t appears everywhere. So this is subharmonic in t, okay? So, but it only depends on the real part of t, so therefore it's even better than subharmonic, it's actually convex. Subharmonic function that only depends on the real part just has positive second derivative, therefore it's convex, okay? So now, in fact, if you look at this thing, this is where I'm going to wave some hands in my final lecture. If you look at this thing, it's sort of starting out as the whole surface, and there's some bound on this norm, it's whatever the Bergman kernel is, okay? But then maybe you sort of, you start moving your parameter, and maybe the bound grows. In fact, we will see that it absolutely does grow, right? But at some point, you get to a situation like this, and the domain is just shrinking down to a disk. So it's not a difficult estimate in that sense to show that this norm C is actually bounded. Okay? So with some basic calculus and with some easy But clever calculus, you show that this norm c squared t star is bounded. Okay, so now what do you have? You have a semi-infinite line, and you have a bounded convex function. So it must be an increasing function. Right? Must be increasing function. So, in other words, you can estimate this. Sorry, it's the other way around. Bounded. No, it has to be like this. Yeah. So, in particular, you have this monotonicity. So, if you want to estimate this norm, you just have to take the limit as t goes to infinity. Okay. So you take that limit, but if after t gets extremely large and negative, you're still always on the whole surface, but your weight is really very much concentrated in the small neighborhood of this thing. And in fact, when you get outside this neighborhood, this quantity becomes positive, and if you make this p huge, the weight becomes huge, so the exponential of the negative of the weight becomes tiny, so essentially the whole norm is concentrated just in this little disk, and therefore you're in this example. So then you can compute the constant, and you see that it's 1 over pi in the limit. And so then you get this estimate. Okay, so that's how the proof goes. So you see the power of this theorem is that if you can find a way to subharmonically degenerate your space into the very simple space, the disk, then you have a certain monotonicity coming from the convexity of this functional, and so you can compute whatever estimate you need in the limit. That, I think, is one of the nicest things I've seen in a long time in complex geometry. So this was Berndtsson and Hilbert who did this. They also did the next thing that I'm going to explain. And it's helpful to have Suita, which is geometrically simpler. This gets more technical, which just means I'm going to explain less of it. But okay. So I hope at least you got a sense of how this works. Yeah. The details are in the notes if you're interested. So. Maybe I should say just beforehand, before starting on the extension theorem, that as far as the extension theorem goes, if you want to estimate the Bergman kernel, it's the extension theorem that you use. Because you're looking, the Bergman kernel is, as we showed in our exercise before, it's the supremum of the pointwise norm of section. So if you can have an L2 extension of this with some particular constant, this is going to be bounded by the norm. So if you start with a section, if you start with this number, you can extend it to some section. You divide by the norms. That will exactly give you the Bergman kernel. And so our constant that we got in the Osawa-Takegoshi theorem was 24 pi. So this would be, instead of pi, we would have 24 pi in the estimate. And so that would be the sort of estimate you would get for, it wouldn't prove the conjecture, but it would give you at least an estimate on the curvature. But if you knew that the sharp constant was pi, then it would be it would also give you a proof of this thing. So that's what I'm going to prove now, that the L2 extension theorem holds with the sharp constant pi, by essentially the same method. Okay. So let me state the version of the theorem that I want to prove. So it's going to be a lot like the theorem we already proved, but it's a bit more constrained. So X is going to be a Stein manifold. Omega will be a Kähler metric. And then we're going to have a function this time. So it's a bounded holomorphic function. So remember, before we had a section and a metric, so that the norm was less than 1. Now the line bundle for, well, I have to define Z. Z, the hypersurface, will just be T inverse of 0. and you assume that dt of x is non-zero for all x and z. So the line bundle associated to z is therefore trivial, and you just use the 0 or the 1 metric, the constant metric, so you get values in the unit disk from this bounded holomorphic function. Okay, so, but this is classically, this was the case treated, just a zero set of a bounded holomorphic function. But anyway, we still have a line bundle over x, so this will be a holomorphic line bundle with metric e to the minus phi, such that dd bar phi plus the Ricci of omega, there's no lambda anymore, so this will just be greater than or equal to 0. Okay. Then the conclusion is that for all f holomorphic on z sections of L, such that the integral over z of f squared e to the minus phi dA omega over the magnitude of dt squared with respect to omega is finite, there exists a holomorphic section of L over all of x such that f restricted to z is little f, and the L2 norm, this time the standard L2 norm of f, is less than or equal to, and now the sharp constant pi. G omega t squared omega. Okay. Yeah. Yes. Yeah, it's for L. Left-hand side of this thing? Yeah. So F is a section of L. So this is just the pointwise square norm with respect to that metric.
I is defined where on the whole of X?
Yeah. And
on L it serves as a
I don't understand the question.
This phi thing, does it live on L or on the whole of
It's a metric for the holomorphic line bundle L.
It is on the whole of X. Okay.
Yeah. There's no LZ now. LZ is a trivial bundle. That's the difference. It's okay. I thought it was something like that. So I thought if I look confused enough, you'll realize that. Okay. So this is the theorem I want to give the idea of the proof of. Okay. So first step is some reductions. So these are reductions we've made before. You can assume that your X is actually a bounded domain in some larger X tilde, and that the metric e to the minus phi, which there could be a singular Hermitian metric, you can assume it's smooth because you can regularize it on any Stein manifold. And we can also assume that F is actually holomorphic up to the boundary. So this Z, maybe T, is also an O of X tilde. And F is actually, and same with L, L extends to the bigger thing, and F is holomorphic up to the boundary. Okay? We've made all these things before, so maybe we don't have to talk about it too much. But so by Stein theory, in other words, the interpolation theorem that we proved, we can extend this F, say it's defined on, we can take X tilde to be the domain of definition of F. It's bigger than X. So this little f can be extended to a holomorphic section on the whole of X tilde. And then when you restrict it to X tilde, because that's a compact set and everything is smooth, you have something of finite L2 norm. So by Stein theory, there exists capital F in gamma O of XL, extending little f. extending just means this. And having finite L2 norm. Okay. So as soon as you have some extension of finite L2 norm, you have a unique minimal extension of finite L2 norm. So thus, there exists a unique so F extending little f and having minimal L2 norm. And it's that f, that minimal L2 norm that I want to estimate. Okay? So far it looks very far away from being applicable, being a thing we can apply Berndtssons theorem to. And in fact, the way we will apply Berndtssons theorem is a little bit subtle. And the reason is that Berndtssons theorem is not quite correctly adapted to this thing, but it is. But you can phrase this problem of finding the minimal norm in terms of a dual problem. So a problem about the dual vector space. So let me try to describe that. So this will be a proposition, which is elementary. It's just linear algebra, really, or functional analysis, I guess. So let me define the L2 ideal with respect to phi of z to be the set of all g in L2, or I guess we had a name for these things, but we don't now. I guess I'll just use, well, okay, let me just do this. L2 e to the minus phi dv omega intersection holomorphic sections. Cauchy had the smarter, you just put the subscript O so you can write less. I don't have that kind of onboard intellect. Okay, so then such that the restriction to z is identically 0. So usually the ideal of something is not global like this, it's just local things. But still, I'm taking global sections in L2 which restrict to z identically 0. Okay? And then this thing has an annihilator in the dual space. So the annihilator of this ideal, not really an ideal, but it still has an annihilator. So this is the set of all c in, let's give this guy a name now. Laziness is the important feature a mathematician should have, I guess. All sections in the dual which annihilate such that this c acting on g is 0 for all g in I phi of z. It's not a proposition yet. Those are just the definitions. And then the claim is so this f now just means the minimal extension. Any other extension I'm going to denote with some f-like character, but it won't be f. Okay. Then the L2 norm of this minimal extension is actually equal to the sup over all, the sup of the numbers. So c capital F tilde squared divided by the norm of c squared star, where over all c in the annihilator, okay, for any extension f tilde L2 extension of little f. So you don't have to know the minimal extension. If you take any extension, which we know exists by the mumblings that we made before, if you just pair it with the annihilator and divide by the norm and take the supremum of the square, you will get the minimizer, okay? So this is the dual problem that we're gonna have to look at. Okay, in fact, working with these guys, with these elements of the annihilator is a little difficult because they're not particularly subject to complex geometry. But fortunately, there's a dense subspace of this annihilator of very much manageable linear functionals. And now I'll tell you what those are. So for any G, so this will be some, say, smooth section of L. So this would be smooth with compact support. You can define C sub G. So what does this do to some F tilde? Doesn't have to be an extension, just any element of the Hilbert space. Well, you integrate over Z F tilde G bar e to the minus phi dA of G over dt squared. G is omega. Okay, so you just integrate with respect to a compactly supported thing. And I claim the collection of such things is dense. So the collection of all such CG, so G is, let's have a notation, G0 of ZL is the things with compact support. So this in the annihilator of I phi of Z is dense. Okay, so remember, this is one of these kind of functional analysis top arguments. If you want to prove that some set is dense, you take a vector orthogonal to it and you show that it must be zero. And so if these guys all annihilate some F, then F must vanish there. So it's in the annihilator. Okay, so it's in I mean, sorry. So this just means that you have density. Well, let's take a look at this action for just a moment. So now suppose F is extended by some F tilde. So let's look at what this CG of F tilde squared is. Well, it's the integral over Z of F G bar, because it's an extension of F, and we're on Z, so you just get F here. E to the minus phi dA sub G over dt squared. Keep doing that. Omega over dt squared. Omega squared. And now this guy's holomorphic. This guy is just smooth with compact support. But you can always write it as something holomorphic plus something orthogonal to the holomorphic. And so the holomorphic thing is you apply the Bergman projection. So in fact, this will just be this Bergman projection acting on G. This is the Bergman projection with respect to this L2 structure. Okay, it's a little different than the one we had before, but in any case, that's what it is. And if you apply Cauchy-Schwarz here, then you get, this is less than or equal to the integral over Z of PG squared e to the minus phi dA omega over dt squared omega times the quantity that we're interested in, F squared e to the minus phi dA of omega over dt squared of omega. Okay, so if you now divide this by the norm of CG squared star, that just comes over here, CG squared star. And so what you want to prove is that this quantity here is less than or equal to pi. Okay? That will finish the proof. Okay, so and this is where quite a bit of technical lemmas come in. Yeah?
The last line of it.
Yeah? Compactly supported. I just said it because I didn't want to spend time writing or answering. Yeah, that's my mistake. I should I do that. I waste time anyway. So, okay. Right. So now, how do you prove? So this now you can sort of see Berndtssons theorem coming into play. So the idea is to try to degenerate the space so that you could estimate this quantity. Okay. And I think I don't want to keep people forever, so I think I won't have time to explain. There are some things you have to do. For example, you have to find an extension of this thing to all of x, which you can't. But what you want is an approximate extension to all of x. And approximate means that it approximates PG on Z with respect to this norm. And that's something you can do. We didn't discuss Runge's theorem, but there's a kind of L2 version of Runge's theorem, and you can find it, for instance, in Hörmander's book or other places too, probably. But there is a kind of approximation involved here, which even in the notes I just referenced that, because it's not in the mainstream of what we want to discuss here. But you need something like that. But maybe you can sort of believe that the main thing you want to do, see, this is already happening on Z. The main thing you want to do is degenerate this thing down to Z. And then I won't show you in that case that it's exactly pi, but, well, maybe I will. Maybe I will without showing it directly. But. So what's the degeneration? So idea, as in Suita, is to degenerate x to z. Okay, so we've lost our Suita family of metrics for Berndtssons theorem. So here I'm going to use capital phi because there's too many little phis. So capital phi t is the family of metrics. Okay, so this is the initial metric phi from the theorem, and then you add the real part of t, and then you take the maximum of log mod t squared minus the real part of t and 0. So you can think of this as acting as the Green's function, except instead of having a pole being a point, the pole is a hypersurface. And getting the bound less than or equal to 1 means that this thing is bounded above by 0, and so all the features will happen, except it won't work unless you really crank up this factor. So then once again, this L2 norm will be supported. If you have your Z, now this is your point in the space of hypersurfaces. It's actually a hypersurface in X. And when you look at this function, remember we're sort of working in some fixed bounded domain. And so if this T is huge negative, you're just going to get some small neighborhood of this thing, and in the limit it will collapse to a kind of product of Z with a disk. And so it's almost exactly the same as the Suita problem, but you can't quite take the limit. You have to do some estimates here to get this correct, to show. But the main thing is that Berndtssons theorem tells you that this denominator, its logarithm is a convex function, because it again only depends on the real part of t, because the weight only depends on the real part of t. And then you have to prove boundedness. That's again a straightforward calculus thing, but it does use that we're shrinking the domains a little bit to get some constants. So you get boundedness and convexity. So again, you get monotonicity. So again, it's an increasing function, so the reciprocal is decreasing. Okay? Which means when you go to minus infinity, it's the worst that it can be. It's the biggest. Okay? So from that, you can actually get the estimate you want, but let me just convince you that if you know that the worst possible constant you're going to get is when the manifold is an infinitesimal neighborhood of Z, then you know what the sharp constant is. The sharp constant is just the area of the cross section. Now this real part of T here shows up in the way does e to the minus real part of t. So t will be real, so let me just write it like that. That is, if you write this as pi over pi, this is the area of the cross-sectional disk. But this is appearing in the norm already. So when you divide by the norm, you will get the constant pi coming up in here. So I think once you know that this is shrinking down to an infinitesimal neighborhood and you're getting the worst possible constant, it's very clear that the constant is going to be pi. So maybe in the last minute, I just want to mention that once you have this theorem, you can actually prove Berndtssons theorem directly. So I'll say in hand-wavy ways how you do that. So when you compute the, where is it? When you compute something like this, the square norm of a linear functional, you're actually pairing it with sections in the original Hilbert space and taking the supremum over all such things. And you want to prove that it's subharmonic. What does subharmonic mean? Well, so far we've only been using it to mean that the Laplacian is greater than or equal to 0. But in fact, there's an older definition which was introduced for non-smooth functions before the theory of distributions was around. And that definition is that the function is less than or equal to the integral, the average integral over a disk. So what you're trying, if you want to prove that this is subharmonic, you need to get that the function at a point is less than or equal to the integral over a disk. And this, I can't say it in a minute, but if you think about it, is an extension theorem. And the fact that the constant is pi in the extension theorem means exactly that you get 1 over pi or 1 over pi r squared when you rescale. That's exactly the integral over the disk over which you're integrating to prove that your function is subharmonic. So it's not so much that it's a sharp constant as what the constant actually is, which is the area of the unit disk. That is the thing that allows you to prove that the log squared norm of the section is subharmonic. And so these theorems are equivalent. And the Suita conjecture is a case where the dimension of x is 1 of exactly the same problem. So they're all the same problem. Everything in the end is some L2 extension problem, at least according to Osawa. So with that, I thank you for paying attention for so long, and I'm done.